Okay, welcome back to Real Analysis. We have been starting with a construction of the real numbers by starting with a construction of the rational numbers. And we're today actually going to construct the real numbers for the first time. So let me just remind you where we've been so far. Last time we discussed our construction of the rational numbers as pairs, ordered pairs of integers. Now, of course, you think of rational numbers as fractions, and fractions are, in fact, ordered pairs of integers, aren't they? Right? You have a number on top and a number on bottom. And the way that we thought about this was, okay, these ordered pairs satisfied some notion of equivalence. And it's just the usual notion of equivalence that you're used to, that you were taught in grade school for how to tell whether two fractions actually represent the same thing. What we've seen is that this is, in fact, an equivalence relation. We've seen that under this definition, we can actually construct an addition and a multiplication that's well defined. So it gives this collection of ordered pairs a structure, an arithmetic structure. Okay, and it has an order, which, if you recall, an order relation satisfies two properties. Do you remember what properties those are? Good. Trichotomy and transitivity. So trichotomy is basically whatever the relation is. If we say it's less than, if you take two elements, x is either, you have exactly one of the following things true. X is less than y, or y is less than x, or x equals y. Okay. And transitivity says that if x is less than y and y is less than z, then x is less than z. Okay, so that's an order relation. And Q, in fact, has a nice order relation, and we define that as well. But the message is, it's exactly what you learned in grade school. Okay, so from here on out, now that we've carefully constructed the rationals, we can think of rationals as fractions. Okay? And it contains the integers in a very natural way. Okay, we also saw that Q, in fact, is nice because not only does it have these arithmetic operations, but it has the ability to solve certain equations that we couldn't solve in the integers before, right? So for instance, 3x equals 5 can't be solved in integers for x. But it can be solved in the rationals because the rationals are a field, okay? And it satisfies certain addition properties, which, if you recall, we labeled by letter A, 1 through A5, and some multiplication properties, M1 through M5. And then a final property, which is the distributive property, which basically says that addition and multiplication have to play nice with each other. Okay? You should be able to multiply. You should just be able to distribute addition over multiplication over addition. Okay? Okay, and we saw that, in fact, the rationals, not only do they have an order, and are they a field, but they're an ordered field, which, in addition to those two things, means what? That the order and the field properties, operations, need to what? Play nice with each other, right? In particular, if I look at two rational numbers and I add the same thing to them, then their order relation should stay the same. Or if I multiply them by a positive number, rational number, then they should still preserve the same order. Okay? Okay, great. So this is what we talked about last time. And we finished by noting that the rationals are not large enough to solve all equations. Okay, so in particular, this equation might come up if you were looking at a right triangle, length 1, and you know by the Pythagorean theorem that the hypotenuse has a length that solves this equation, x squared equals 1 squared plus 1 squared. And yet, there's no solution to this equation in rationals. This is what we discovered last time. Okay? Okay, so what is our plan for today? Our plan is to begin to rectify that problem by looking for a construction that would allow us to solve equations like that, x squared equals 2. Okay, so here's the plan for today. I want to construct the real numbers. Okay. And in particular, I want to show you a construction due to Dedekind. These are called often called Dedekind cuts. In 1872. There are actually several ways to define the real numbers formally, but this is one that we'll use because it only involves the kinds of ideas we've discussed before. So what do I mean by construct the real numbers? Well, here's the idea you should have in your head. If I remember have a number line, because we have an order, we can place the rationals along this number line. So for instance, here are the integers, right? And then here are some rationals. Okay. A few of them, right? Not going to write them all, obviously. Okay. And, well, what do I have? I have here, maybe there's a number line. Here's some of the integers. The rationals are in orange. But there are some holes in some sense, right? If the Pythagorean length, square root of 2, what we're calling that the square root of 2, we actually haven't defined what we mean by square root, but if you look at the hypotenuse with side lengths 1 and 1, it's a length along this line, and yet there isn't a rational that spans that length, so this might be the hypotenuse. That's the hypotenuse length of this particular triangle. And yet, if we look for this particular length here, we have a problem. There is not a orange point right there, in some sense. Okay, so this thing has holes. So, what does it mean to construct the reals? Well, what I mean is, I want a construction that only depends on things I've already defined. Just like the rationals, how did we construct those? We define the rationals in terms of integers, okay, as ordered pairs of integers, but in a fashion that only depended on the things we defined before. So if I wanted to define the real numbers, I can't say let's fill this in because it doesn't even have any meaning. What does it mean to fill in this line? I don't even know where the holes are, right? So how will I get at the fact that I have some gaps here without talking about the gaps? Okay, do you see the problem here? That's the question. Okay, there are a few ways to do this, but that's the question. So, any ideas? How might I get at the fact that there's a gap here? Let's see. Well, here's one way to think about what's going on. If I look at all these rationals here, okay, so maybe x squared equals 2 does not have a solution, as we've seen in Q. Okay? It might be worthwhile, then, to look at the other possibilities. What about, and the mathematical way of saying what about is to say consider. Okay? So you're telling your reader to consider, to take a look at something. Okay? Consider, let's look at the following set. How about I look at the set of all, I'll call this A, the set A. It consists of all x and q such that x squared is less than 2. Because this equation, x squared equals 2, if it's not true, then either, for a given x squared is less than 2, or x squared is bigger than 2 by trichotomy, right? So let's just look at one of these things. That's all the numbers where the square is less than 2. What does that look like in this picture? Okay. Is it all the rationals? Is it all the rationals to the left? What about minus 100? Yeah, it's not quite. Well, actually, it'll go even a little farther, right? It'll go somewhere out here. But this is certainly a set that that is this set A. Okay. Oh, so it's actually not this interval, right? It's all the things inside, all the red. It's all the orange points inside, right? Okay. Okay, so if I take a look at this set, it has an interesting problem. Okay, what's the problem? The problem is if I look at this and I look at the points to the right, the problem is there is nothing right here at the very edge, right? I wish that there were, but there isn't. With me? I wish that there was. Okay, so this points to a property that we want to get at. Okay, and so we'll give it a name, and then we'll explore what it means for our construction. And it points to the idea that of what's called a least upper bound. Now, what do I mean by that? If you take a look at this number line, the fact that there isn't a point that's right at the very end is it's related to the idea that, okay, there's a bunch of points to the right, aren't there? There's just not one at the very end. All the points to the right have the property that what? Like if I look at the number 2.2, how does it relate to all the numbers in A? It's bigger than all of them, okay? We have a name for that. We'll call 2.2 an upper bound, okay? And it's an upper bound if it's bigger than everything in the set. So is 3.1 an upper bound for this set? Yeah. Is 1.5 an upper bound? Yeah, if you maybe think about it a little bit, we'd have to show that. But we have an upper bound. And the idea we're trying to get at is there a least one? And the problem is, in Q, there may not be a least upper bound. Okay, so let's write this down. So here's a definition. Let's suppose we have a set that's ordered, and we take a look at a subset. So suppose I have a E, it's a subset of S, which is ordered. S is the big set, E is a subset, like that set we were considering. So if there is a number that has the property that anything in the set is less than that number, we'll call that number an upper bound. So if there exists, let's say, a number, I'll call it beta for bound. Okay. If there exists beta in S such that for all x in E, we have x less than or equal to beta, then we'll call beta an upper bound. Call it an upper bound for E. And we'll say E is bounded. If it's unclear what you mean by bounded, we'll say bounded above. Okay, usually you want it to be both bounded above and bounded below to be bounded. So maybe I'll just make sure we're explicit, and we'll say it's bounded above. Okay? Okay. Good. Now, there's also the corresponding notion of a lower bound. So take a guess as to what a lower bound might be. how would I change this statement? Yeah, just replace less than or equal to by greater than or equal to, and you get the definition for lower bound. So I'm just going to mention that here, the idea of a lower bound. Replace. So to define a lower bound, replace less than or equal to by greater than or equal to. Okay, parenthetical comment. You could talk about being bounded below. Okay, everybody happy with that? Now, what I want you to notice here in this definition is it's saying what we just said, but a little more formally, right? So all we're saying is there a number that's bigger than everything? So to say that formally, we say, well, if there is a number that is bigger than everything, then it's an upper bound. Okay, I want to point out, because this notation comes up a lot, these particular phrases come up a lot, is that we have a shorthand for these phrases. Many of you know what the shorthand is. What's a shorthand for there exists? It's a backwards E, and the for all, it's an upside down A. Okay. These shorthands are appropriate for scrap work or board work. They're not appropriate for writing out mathematics formally. Okay? So you should avoid it when you're doing your homework, but it's okay to do it if you're just trying to show a friend something. Okay? And hopefully we're friends, right? So I can use these, okay, on the board. But if I were writing this out on the solution set, I wouldn't use these phrases. Okay, good. We have a notion of an upper bound, and so let's maybe just do a few examples here. So we've already said that for this example. Okay, so what did we say? We said 2 is an upper bound for the set A that we just defined earlier. Okay. Now, how do we know, actually, 2 is an upper bound for A? In fact, it was maybe a little less clear whether 3/2 is an upper bound for A. So you might ask yourself, why? Well, if it were not an upper bound, proof by contradiction, if not, I mean, what's the property to be an A? Everything in A is square less than 2. So what does it mean for 3/2 to be an upper bound? Well, 3/2 squared is bigger than 2, but why does that mean that it's an upper bound for everything whose square is less than 2? Why would that be? Why would that be the case? Give me an argument. Yes, Steve?
Because if it's not an upper bound, that means there's going to be an x in A that's greater than 3/2. And since 3/2 squared is greater than 2, that means that x is squared would be greater than 2.
Okay, good. And why is that? Okay, so if not, it's not an upper bound, then there is an x, so maybe there is an x in A, such that x is bigger than 3/2. We've already verified that, okay, so it's not an upper bound, then something is strictly bigger than 3/2. Then what would be true? Steve is saying then x squared is going to be bigger than 3/2 squared, which would be what? Bigger than 2. You can check that that's bigger than 2. And then x could not have been an A, which is a contradiction. X is an A, not an A, contradiction. Okay, now I just did this to illustrate a point. To illustrate this how we really know this. we're not going to, carefully check everything. I want to point out also, this is another shorthand that you use, and you should not use on your writing in your homework. This symbol, which means what? Implies. So in formal writing, you should write out implies. Okay. Okay, so this shows that, in fact, 3/2 is an upper bound. If there was any question about it, we can check it. And this property is just a property that it follows from the fact that multiplication plays nice with order. Okay. Yes? I don't see. Okay, so the question was, for those listening at home, do we need something to exclude negative numbers? No, because if x is bigger than 3/2, if there is an x that's bigger than 3/2, x is actually positive. Yeah. So we don't have to worry too much about that. I mean, then you'll be basically multiplying on both sides by something positive. Yeah, all we're verifying is whether 3/2 is an upper bound, and if it's not, then there's something bigger than 3/2, which is already positive. Yeah, we will have to worry about those negative issues in a little bit when I start talking about cuts. Okay, good. So we have an upper bound. Let's define least upper bound. So the least upper bound better satisfy two properties. Just take a wild guess. What the least upper bound? It's a number that what? Is an upper bound, and it's the least of all of them. Okay, very good. So let's say that formally. So if there is a, let's call it alpha in S, such that first property, alpha is an upper bound. I'm abbreviating upper bound now by UB of V. And second property is, what does it mean to be the least upper bound? Anything greater? Let's see, if 2 is an upper bound, certainly things that are bigger than 2 are still upper bounds. Okay, good. So you want to go the other way. So if anything is smaller than alpha, then it better not be an upper bound. Excellent. So we'll write that down. And if gamma less than A implies gamma is not an upper bound for E, then alpha is called the least upper bound. And we often abbreviate this by LUB, lub. That's the least upper bound of E. Actually, there's a name that's even more used than this, and that is, we sometimes call this the supremum of E. And we write alpha equals sup E. Okay, the supremum of E is the least upper bound of E. Okay, and of course the word kind of suggests that to be supreme means to be bigger than everything, right? But it's the least biggest thing. Okay, so it's sort of what might be at that endpoint if there were something there. Okay, so let's explore that concept a little bit as well. Which sets have suprema? Let's do some examples here. Okay, so let's just take, throughout all these examples, let's take, I'll just let S be the rationals, S equals Q. Okay? Throughout all the examples. So let's consider the following set. What if I take the set E consisting of these numbers, 1/2, 1, 2? Does it have a supremum? What is it? It's 2? Justify that for me. Justify that for me. Why is 2? First of all, is 2 an upper bound? Malus. Very clearly. Good, it's an upper bound. Great. Why is it the least upper bound in terms of the properties? Harris.
Suppose there were some upper bound less than 2, then 2 would be greater than that upper bound.
Good. Does everybody, so what Harris said was, suppose there were an upper bound less than 2, let's call it gamma. Well, then gamma wouldn't be bigger than 2. And therefore, it's not an upper bound for this set. Everybody happy with that? Okay, good. So let's generalize a little bit. This is one example, but suppose I throw in another number. Suppose I throw in the number 1.5. What's the supremum? 2. Suppose I throw in another number, like 15. What's the supremum? 15. Okay, I could keep throwing in numbers. Can you generalize? Can you come up with maybe a more general statement about collections of, let's say, finite numbers of things? Do finite collection of objects have a supremum? Yes, it's the thing that is biggest. It's the last one on this number line, right? Okay. So in fact, you can see that finite. So we'll just notice this observation: finite sets have sups. Have a supremum. Have a sup. Okay. Okay. Let's take some other sets that are not finite. How about let's look at the set of all rationals that are negative. Q minus, the negative rationals. First of all, does this have a supremum? What is the supremum? 0? Really? Why? How do you know that there isn't like some eensy number that's just to the left of 0 that's bigger than all the negative rationals? You can find a negative number bigger than it, right? So here is 0. Here's all those rationals. And if there were a gamma that's just to the left of 0, then wouldn't you agree there's a rational in between? Okay? In particular, you could find a rational. If gamma itself were rational, which it should be because this gamma should be in the set, right? You just take gamma over 2, and that's something that's closer, that's bigger than everything. With me? Okay, good. So 0 is an upper bound, and it's the least such. So here's an infinite set. It actually has a supremum. What about if the set is, in fact, all of Q? Does it have a supremum? No? No upper bound? Yeah, that's true. That's true. It has no supremum. But we actually, you'll see later, we actually have a word for this. So the reason it doesn't have a supremum isn't that it failed property 2. It's that it failed property 1. That there isn't a upper bound at all. It's unbounded, right? It's unbounded above. And we often write this, later on we'll see, we actually have a way of saying this. We often say sup E is, we use the symbol plus infinity, okay, which doesn't mean anything, okay? It's just a symbol. It's just a way of saying this. Okay? It's very different than this situation. Look at the set A. The set we defined before. What's the supremum of the set A? Does it have a least upper bound? How many people say yes? In Q. Well, Q is all there is. Does it have a upper bound? Least upper bound? What do you think? How many people say yes? How many people say no? Okay, yeah, so it does not have a supremum, but now how do you prove that? Not have, does not exist. And it's not because it's unbounded. Does not exist even though it is bounded. Right, it's bounded by 3 halves. So this is a more essential kind of failure to have a supremum than this one. Okay, so how do you prove this? Well, I encourage you to see the book because there's a proof in the book. But let me just give you kind of the basic idea. I mean, the basic idea is the following. If you were trying to find a supremum, well, you know, A is lots of upper bounds, right? Whatever this set A is. Let me just notate that here. Here's the set A. Whatever it is. And as we saw before, there are lots of upper bounds, right? 3 halves is an upper bound. Okay. So let's suppose you have an upper bound, whatever it is. If it doesn't have a least upper bound, then one way to show it doesn't is to show that no matter what upper bound you give me, I can always find a smaller one. So can you suggest a way to find a smaller one? If you give me any upper bound, I don't care what it's called, let's call it P. And remember, you know, there are a bunch of points in here. Can you suggest a way to find something that's in between this very edge here and P? Well, if you're looking at the other example here you take gamma and 0 and you take their average, gamma over 2 would work, right? Because gamma is rational, right? So what would you suggest here? Take the average of what? Uh-oh. Yeah, so there's a temptation. The temptation might be to average P and the square root of 2, but we don't have a square root of 2, right? Got to be a little careful, okay? And so really, because you can't do that, you have to be a little more clever. And I encourage you to read the book's proof to see exactly how to be clever, okay? So what the book does is, and this is what maybe you don't see. I mean, the motivation this would have been the naive thing, P over square root of 2 over 2. But this is not in the book. But there's a reason this isn't the proof. It's because it's square root of 2. We don't have a notion of square root of 2 yet, right? So what the book does is something slightly different. The book suggests taking a new lower bound to be P minus a little bit, okay? And the minus a little bit is something that only involves P, thankfully, and is rational. P squared minus 2 over P plus 2. Okay? And this, if you work it out, turns out to be 2P plus 2 over P plus 2. And it's enough to get you what you want. It produces a Q that's somewhere in between. Okay? Yes?
I know we haven't introduced what square root of 2 is, but theoretically, if we were to define the square root of 2, couldn't that be a supremum for the set?
Yes, that's correct. But we have not done it yet,
Okay.
right? So we're
Showing that there's no rational supremum for the set.
well, this is showing that the supremum there is no supremum because to say that the set has a supremum means that you're looking for an upper bound that's in the set. Okay, so it has no supremum in Q. It will have a supremum in R. An upper bound must be an element of the big set. And the big set here is Q. Okay? Excellent question. Okay, and that's part of the point. The point is we have a problem and now we're trying to fix it. How are we going to fix this problem? How are we going to get sets like this one to actually have an end if we can't talk about the end? Okay? So that's where we're at. So let's see how to do that. And we're actually ready to do that. So we have this notion now of a least upper bound, the supremum, and whatever we do to construct the reals, it'll turn out the reals, unlike the rationals, will not have sets that don't bounded sets that don't have suprema. Okay, that's the surprising thing. So here's what we're going to do. We're going to construct R. So we'll do this. We'll construct R only involving rationals, and we'll do so in such a way that it'll be obvious that it has the least that it has what's called the least upper bound property. Okay, so we'll construct R and then prove. This is probably the biggest idea that. Well, so here's the theorem. The big theorem. In your book, in Rudin, it's theorem 1.19, 1.19. R is an ordered field. Just like Q, it's ordered, and it's a field, and they play nice with each other, with what's called the least upper bound property. I have to tell you what that is. And R, not only does it satisfy these properties, but it extends Q. It contains Q as a subfield. Okay, so there are three things we are going to show about our construction. Number one, it's an ordered field. Number two, it has a least upper bound property. Number three, it extends Q. So let me tell you what the least upper bound property says. Well, it says basically this last situation can't happen. If the supremum doesn't exist, it's because it's unbounded. It won't be the case that that bounded sets won't have a supremum. So the least upper bound property. So a set S has the least upper bound property. Another way to say this is you might also hear this term, S has least upper bound property, or you might say it satisfies what's called the completeness property, or completeness axiom, if every non-empty subset of S, non-empty is important, subset of S that has an upper bound also has a least upper bound. That has an upper bound also has a least upper bound or a supremum. Okay? Or so a supremum in S. Okay, it has to have one in the set you're talking about. Okay, these are the two most important ideas of what we want to get out of this lecture. So, how are we going to construct R? Yes.
So why is non-empty important if we're also specifying that it has to have an upper bound in the first place? Doesn't the empty set have no upper bound?
So
Or is everything an upper bound?
Excellent question. Let's just see if what's true about the empty set. So suppose you have an empty set. E is the empty set. Let's just ask the question, is 2 an upper bound for E? Well, does 2 have the property that for everything in the empty set, that thing is less than 2? Yes. So everything is an upper bound for the empty set. Okay? Why is it true? This is vacuously true because there isn't anything in the empty set. Are you with me? Since there's nothing in the empty set, we don't have to check this condition. So it's automatically true. Okay? That excellent question. Okay, very good. So I've laid perhaps the groundwork and the foundation for why we are worried about the rationals. How are we going to construct R completely from Q? Let's take a couple-minute break, and after the break, we will begin to define Dedekind cuts. Remember, our task is to construct the real numbers in a way that only involves the things we've defined before, namely the rationals. So how is it that we're going to get at the idea that there ought to be something right on the edge here, right on the cutting edge here? How are we going to get at that idea? Well, the idea of Dedekind was to think about the real numbers as just being some collection of rationals. Okay, just like we thought of the rationals as an ordered pair of integers, we'll think of the real numbers as collection of rationals that are specified in some sense by this cut. Okay, we're going to make a cut right here, and we're going to say that everything to the left, everything, not just this interval of things, but everything to the left is a collection of rationals that will be called a cut. Okay, so here's Dedekind's construction. We're going to define a cut. And we'll denote it by the letter alpha. A cut alpha is a subset of Q. It's not any old subset. It satisfies 3 properties. Okay, so a cut is a collection of these orange points that satisfies 3 properties. The first property is that this collection better be non-trivial. So it's not empty, and it's also not the whole thing, not all the rationals. Okay, so a cut is, this is often referred to as a cut is non-trivial. Okay, don't want it to be nothing, don't want it to be everything. The second property is a cut will be a collection that is, in some sense, closed downwards. And what do I mean by that? What I mean is, if you take anything in this collection, so if you take a little p in alpha, where little p is something in this collection, so take one of these points, then anything that's also one of those points, and to the left of P is also in alpha. So if P is in alpha and Q is in Q, and Q is less than P, then Q is also in alpha. So this is what sometimes you hear the phrase, it's closed downwards, or closed to the left. Okay. Everybody with me on what that means? Okay. And the last condition is that it, in fact, is, in some sense, it's like this picture. It does not have a biggest member, no largest member. So if P is, little p is in alpha, and then little p is less than r for some r in alpha. So this is just saying there's no largest member. In other words, there's something to the right of little p that's also an alpha. This is what a cut is. So it's called a Dedekind cut. So let's see some examples. So here's a question. Is the set A we defined before a cut? No. Which property does it not satisfy? A from before. The set A from before is not a cut. Does not satisfy 2. Fails 2. It's not closed downward. Okay. What about this set? How about alpha, all the negative rationals, q sub minus? Is it a cut? First of all, is it non-trivial? Yes, it's non-trivial. Is it closed downward? Very clearly. And it's got no largest member. Would you agree with that? If you take any negative number, is the negative number bigger? Yes. Good. Is a cut. Excellent. Okay. What about this set? Beta. Let's let beta be all rationals in Q such that R is less than or equal to 2. So picture it's everything including 2 to the left of 2. Is this a cut? No, why not? Yeah, it fails 3. Okay, so I think you have some idea of what cuts ought to do just by the properties. Now, of course, you don't necessarily even know what kinds of things could be cuts, right? But you know it has to satisfy these 3 properties, okay? So I'm just going to declare that we'll just look at the set of all cuts and call that the real numbers, okay? That could be a little puzzling and come across as a little strange. So let's let R be basically the set of all such cuts. This is our definition. I'll define R to be the set of all alpha, where alpha is a cut. There. That is our definition of the real numbers. What? It's a little strange. A little strange. But the point is, once we prove properties about real numbers that we're comfortable with, then we'll just think about the reals like we normally do. Okay? But for now, what do you think the cut is that's going to correspond to the square root of 2? Let's start easier. What do you think the cut is that's going to correspond with the number 1? How about cutting this thing at 1 and looking at all the rationals less than 1? Good. What's the cut that's going to correspond with the number 3? All the rationals to the left of 3. Good. What's the cut that's going to correspond to the square root of 2? That the hypotenuse of that 1, 1 triangle. All the rationals that are in some sense to the left of this creature, so it might look like A, but it better include what else? All these rationals. Okay, that's kind of the idea. Okay, so let's see that this actually behaves like we expect it does, and that's maybe the surprise. So if I wanted to cut to the chase, that's really where we're going, right? It is going to satisfy all the good properties that we expect the real numbers to satisfy. In particular, it'll be an ordered field with the least upper bound property, and it will contain Q. Okay, so the first thing we maybe should do is define what the order is. That's probably the easiest thing to see. So this is a structure, right? I've already just declared this to be a set, but now we have to say what structure it is. So this is some set, but we claim, we'll show, it has structure. In particular, it's going to have an order, it's going to have arithmetic, and the field operations. This is this is where we're going. So I'm going to define an order in the only natural way you might expect it to define the order. Let's define the order. So if I have two cuts, what are these really? These are collections of rationals that kind of look like everything to the left of some stuff, right? Although there isn't really a point here that we can refer to, so that's why we refer to it by these three properties. Okay, so here's a question for you. What's the natural way to define an order? Let me show you two cuts here. Here is alpha, here is beta, and alpha kind of looks like this, and beta kind of looks like this. How would you define cut, Rebecca? Sorry, order. How would I, when should I say, thank you, when should I say alpha is less than beta? Okay, that's one way to do it. I mean, that's one way to think about it, but there's probably an easier way to say it because of some of these properties that we have. I mean, for instance, if you're saying, we'll say alpha is less than beta if there's something here that's not here, but there may be an easier way to say that. Yes? If there's an element of beta that's not in alpha, that's what Rebecca said. Is there an easier way, Steve?
You could show that there is an upper bound of alpha that has an element of beta that's greater than alpha.
Okay, there's no need to show anything. We're making a definition. So what are you suggesting? I have two cuts. Let's define alpha to be less than beta if what's true? Thank you. Very good. A very simple definition. So we'll define the order. Alpha, we're going to say alpha is less than beta means alpha is contained in beta and it's not equal to. So it's properly contained. Okay. By the way, I could have written this, say alpha is less than beta if alpha is less than or equal to beta, but I don't really mean if, I mean if and only if, right? I mean, I'm making a definition, right? So that's why I wrote the word means. Yes? Mm-hmm.
So even if you put all the cuts together, you still are left with everything you started with, all the rationals.
Yeah, what do you mean by put all the cuts together? Do you mean unioning the sets of rationals?
Yeah. Well, like if you had the cut from everything to the left of square root of 3, you go over the square root of 2. But like there's like a cut from the square root of 2 as well, but you never actually like have the square root of 2 in the set. The square root of 2 is the real number.
Okay, so the question was, if you have something that's supposed to correspond with our notion of the square root of 3, does it contain the square root of 2?
Well,
The thing that corresponds to the square root of 2?
like you said, the reals is equal to this set, but that set doesn't contain some numbers that can be numbers.
What numbers? Oh, I see what you're saying. In other words, where is the square root of 2 in this set? The thing that's supposed to correspond to the square root of 2. Haven't said that yet, but I'll just hint at it. It is exactly it will exactly correspond to the rationals that are to the left of the square root of 2 in the way you normally think about it. But the point is, I don't have to talk about, I don't have to refer to the square root of 2 in making this definition. Okay, so I'll try to be more explicit about it once we get there, but the idea is, you remember this set that had no least upper bound in Q? Well, guess what? It'll have a least upper bound in R once we talk about how to take least upper supremums over here. Okay. Okay. Yeah. Excellent question. It's a little while to wrap your head around this. It's quite amazing. Okay. So First of all, is this an order? I'm not going to do this part. I'm just going to say check that it's an order. Trichotomy. Is it possible for alpha to be less than beta and beta to be less than alpha? If this is a proper containment? No, clear, okay, right? And the only way they're equal is if there is exactly equal containment. Does it satisfy transitivity? Clear, right? But you should check. Okay, it's an order. Very good. What else? Well, I want to know, does it have an operations that I can deal with? And that's the amazing thing, is that we can actually define an operation. You tell me how to define addition. Let's see, I think I want to keep those boards for now. How should I define addition of cuts? Remember, a cut is a collection of rationals. So I'll give you a picture here. Here is, this is alpha. This is beta. This other collection. So how do you think we could define a new collection, which we will call alpha plus beta? A new collection of rationals. Now, maybe one of the rationals here is 3/2. Maybe another rational here is 2. Yes? Excellent. So one of the things here should be 2 plus 3/2, 3.5, right? But there should be a lot of other things too. Add all possible pairs, and that's a set of rationals, isn't it? So addition. Let's define alpha plus beta to be, sometimes we write colon equals. It means define, it's a definition equal. You do this in computer science, perhaps. To be the set of all R plus S, such that R is in alpha and what? S is in beta. Period. Okay. Oh, interesting. Is this a collection of rationals? Yes. Is it a cut? Oh, something to check, right? So you have to check that it's a cut. Let's think through whether this makes sense. Check it's a cut. First of all, is it non-trivial? If there's something in alpha and something in beta, isn't there something here? And if this isn't everything, is it clear that this can't be everything? Yeah, you'd have to check. So if it's not everything, then this has an upper bound. Let's call it M. This has an upper bound N. Then I claim, is there something that is an upper bound for this? M plus N. So it doesn't contain everything. Okay? With me? Okay. It's let's see. Is it closed downward? Something to check. And if we were to do this just thinking about it, why is it that if you have a point here, a rational here, everything to the left is also in the collection? Interesting. So maybe I'll do this just to give you a sense of how it goes. So check that it's a cut. So the first thing is it is clearly non-trivial. Non-trivial. I'm just going to tell you to check that. Second thing is it's closed downward. Well, the key idea here is we're just going to, so if you have, let's say, something in alpha plus beta, let's call it little p in alpha plus beta. Let's take something smaller. So let's say, let's say Q is less than little p. Well, if P is in alpha plus beta, would you agree that little p is the sum of two things, R plus S? where R is in alpha and S is in beta. Agree with that? Okay, this is in your book, so you don't need to write it down, but if it helps, just follow. Would you agree so I'm now looking at Q and I want to know, is Q also an alpha plus beta? Well, what does it mean to show that Q is an alpha plus beta? I need to write Q as the sum of two things. Something in alpha and something in beta. I know P is the sum of two things, R and S. Okay. Well, would you agree? So notice, oh, this is a neat observation. If I take Q minus R, would you agree that because Q is less than R plus S, Q minus R is less than S? Oh, but Q minus R is less than S. What does that mean? Actually, I have it written in my notes backwards, so let me do this. Q minus S is less than R, just to agree with my notes. Well, what does this mean? Q minus S is less than R, but R is an alpha. So where's Q minus S also in? Because alpha is closed downward. It's also an alpha. So Q minus S is an alpha. Then, so this is the beauty. Here we go. Q is, isn't it really just Q minus S plus S? Where Q minus S is in alpha and S is in beta, right? As desired. This is a good way to end a, when you end with the words as desired, you're reminding the reader that you've shown something you were asked to show. Okay, and you say, reader, you go back and remember what it was you're asked to show. Okay, all the proofs they look like this, okay? They're cut from the same cloth. Okay, they all look like this. I'm not going to do the other one. So here we go. Close downward, and what was the other one? No largest member. Check. It's a cut. Great. Okay, so we have an order. We have an addition. We would want to show the properties, show the axioms for addition. Show the axioms, A1 through A5. And again, I'm not going to do all of these. I'm just going to have you think through why they should be reasonable, and you can check them in the privacy of your own home. So, for instance, commutativity. If I define beta plus alpha to be all S plus R, such that blah, 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 is it clear that alpha plus beta is going to be the same collection as beta plus alpha? Why? Addition itself is commutative for rationals. So commutativity for reals follows from that for rationals. Nice. Okay. Associated property, same idea. So that's A2 through A5. Is it clear that, the first one is that it is a cut. So we've just done A1, right? So that's A2 and A3 are the commutative associative properties. Additive identity and multiplicative inverses. Oh, so we should at least say what those are. So what's the additive identity? Let's give it a name. We'll call it, I don't know, how about 0? We'll just put a little star there to remind ourselves it's not the number rational 0, it's a collection. What should play the role of 0 in tonight's play? Good, the set of all negative rationals, Q minus. Oh, okay, that's cool. So you should check that alpha plus 0 star equals alpha as cuts. But what does this mean? These cuts are sets of rationals, collections of rationals. So really what this means is, so verify, well, how do you verify two sets are equal? you could show that one contains the other. You verify that alpha plus 0 star is in alpha, and alpha is in alpha plus 0 star. Okay? Let's talk through that as well, and you'll see in your book why it's true. If I take something in this collection alpha, and I add something from 0 star, which are what? Negative rationals. Is it clear that it's still in alpha? Yeah, because you add anything negative to a number here, it only gets smaller. Why is that still in alpha? It's closed downwards. Beautiful. With me? Okay. Let's go the other direction. Why is it that if I pick something in alpha, in this collection, it's the sum of something in alpha plus something negative? Member. Okay, good. So what you're saying is, because there's no largest member, you can write alpha. So here's the thing that's in alpha. That's in alpha. Here's P. Because there's no largest member, take something, let's call it Q, and we'll write P as Q plus the Q minus P. P is Q plus Q minus P. That's the basic idea, right? And this is the thing that's in 0 star. Now you have to be a little careful here. So you have to check this, right? But this is the way to go. This is a proof sketch, literally a sketch. Okay. Now what we didn't want to encourage you to do though is practice writing this argument out and then check and see if the book does it the way you did it. Okay. Excellent. Other thing we should probably say is, what is an inverse? The additive inverse. This is a little more complicated. It's not obvious what this should be. So if you want to talk about the inverse for alpha, so here's the picture. Here's alpha. It's all these points here. Now, how would you find its inverse? What would play the role of minus alpha? So let's say here's 0. What would play the role of minus alpha? Well, there's part of you that kind of wants to just invert this thing, right? But then you get something that goes off to the other side, right? So you have to be a little more careful. So I'm just going to say, and then I'm going to throw up a definition that's going to look unmotivated, but it's motivated if you think about it. It's going to consist of all rationals such that there is a number, r, bigger than 0, such that minus p minus a little bit is no longer in alpha. And your job then is to show alpha plus beta is 0 star. Okay, so we're looking at all collections of rationals. So in this picture, beta, oh no, I just lost my chalk. Okay. It fell in the recesses down here. We're just going to look at all the rationals which have the property that when you look at anything, if you look at minus p, you can subtract a little bit and it's not in alpha. Okay, so let me give an example. Here, it kind of looks like this picture. This is going to play the role of minus alpha. Why? If I look at this point, minus p is over here, and if I subtract a little, I'm still in alpha. So this is not in minus alpha. On the other hand, this point will be in minus alpha, because if I look at its negative, here's p, here's minus p, I can subtract a little bit and it's still not in alpha. Okay, but this is the creature that does the thing that you would want. All right, that's addition. Let me close with multiplication and finish with what the least upper bound is going to be. So I'm going to erase this here because it's convenient. So multiplication, I'll just make a few comments because it's kind of what you might expect. If addition is the sum of two things, one from one cut and one from the other, and you look at all such things, what do you think multiplication ought to be? Maybe the products of lots of things, one from the other. Only problem with that is that if you have some negatives, you run into problems, right? Negative numbers. Okay, so the definition for multiplication, you just have to be careful for about minuses. So I'm just going to say this. Just be careful of negative rationals, when they multiply. So the definition looks something like this. I'm just going to first define it for the positive rational. So define if alpha and beta are in the positive reals, the ones that are bigger than 0, alpha bigger than 0 star. These are alpha and beta are bigger than 0 star. Then alpha beta is defined to be the set of all little p such that instead of saying p is equal to some product, we'll say p is less than rs for some r in alpha, s in beta, and rs bigger than 0. So here we're just being careful about using only positive rationals. Okay. And we'll let 1 star be all the rationals that are strictly less than 1. That's the multiplicative identity. And then I'll let you look at the book to see what you do for negative numbers. For negative reals, basically you make them positive, you multiply, and then negate as needed. See book. And the claim is, and you can check all these things, but we won't do it, it's just tedious, is that this satisfies the multiplication axioms as well. Okay, and so now, just to finish, let me just then say, does this have supremum? Does this creature that we've just defined have suprema? How would you take the supremum of a bunch of cuts? And I'll give you a hint here. Look at this cut. Look at this cut. Oh, I have a whole collection of cuts. What's the cut that's going to be like right that does a thing that contains them all because it's bigger, but it's the smallest thing that contains them all? What's the thing you might do? Here's a bunch of cuts. Here's one. Here's one. Here's one. Here's one. Here's one, and it's all these points here. Take their what? Take their unions. Beautiful definition it's a beautiful description of what the supremum ought to be. So, given a bunch of cuts, so if alpha is an A, so given A, a set of cuts, a set of cuts A, let's let gamma be the union of all the alpha where alpha is an A. And the claim is, this is what I'll finish with, gamma is going to be the supremum of A. And it's a cut. Gamma is a cut, and gamma is the supremum of A. It should be very clear why it's an upper bound, because it contains everything else. and we'll have to see why it's a least upper bound. And once we do that, we'll have very easily shown that R has this property that Q does not have. Okay, it's complete, has all its holes filled in. Okay, we'll say a little bit more about this next time. Have a great